Hey, physics fans, this is Physics 12, Momentum, 2 dimensions. We have the lessons complete and under our belt. Sharpen up your pencils. Let's just go over some of the homework questions that I'm going to ask. And then I'll have another video up shortly. I mean, real shortly, since I already have all the answers. So let's just go over number one. This is on page 91 and 92, I believe, in the workbooklet. Hockey player of mass 82 kilograms is traveling north with a velocity of 4.1, and then he collides with another hockey player, 76, that's traveling at 3.4 meters per second. If the two players lock together momentarily, in what direction will they immediately be going after the collision, and how fast will they be traveling? Okay, so that's just a simple, again, right angle one, because it is north and east. So one person's going to be going north, the other one's going to go east. They'll stick together momentarily and go off in this direction. So you have to find out this momentum, and add them together because they're at right angles. Get that guy's momentum and then divide by the total. It'll be easy, pretty good. Next question. Number 2. A car traveling west is hit by a truck going south. Oh, goodness gracious, and they lock together. Like the last question, don't need to talk about it. Question number 3. Let's see. One thing that is difficult, okay, they're talking about is that there is no compass headings here, just relationship between the pieces. Okay, I just put that note in here. This is a little tougher question here. A frustrated physics student, oh, that's most of my students, blew up her physics textbook using a small amount of explosive. Ooh. It broke into 3 pieces, which miraculously flew off in directions that were all on the same geometric plane, because we just want to leave it to 2 dimensions, not to 3. Okay, so at that point, a 0.2 kilogram piece flew off at 20 meters per second. That's an explosive. And a 0.1 kilogram piece went off at 90 degrees to the first. See what I mean? Boom. You don't have any directions, but you know that they're making a right angle there. To the one that's going at 30. So this one's going at 30 and this one's that. What's the momentum of the third piece? So before it blew up, there was no momentum, period. Poof. And then this is good. Then there's the conservation moment. It's a good question. And then you get the momentum. And then you find it, after that, you can find the mass of the third piece if you want to find out the velocity. But you don't need this to find out the momentum. Good question. Again, a right angle one, but it's a little bit difficult because there's no north, south, east, west. What do you do? Well, you figure it out. Try it out. Or just guess a direction. Now, this question number 4 shouldn't be in the book at this location because it requires a bit of energy stuff. But it's telling you that the collision is perfectly elastic where there's no kinetic energy lost. And you go, so why? Is that just information that you don't need? No, we need it, and it's very important. And using the fact that the first proton is moved 30 degrees from its original path after the collision, figure out the speed and direction of each proton afterwards. So a proton is striking another proton, and it's called obliquely, meaning that they hit and then they go off. Okay, now they say that this angle here is 30 degrees. So it hits and deflects 30 degrees from its initial path. So you need that. And then you have the masses of all the objects, and they're all the same. Makes it actually easier, considering it's a bonus question. And you know the speed of this guy. So you know the momentum of the system. And you know the kinetic energy of the system. If you don't remember the formula, kinetic energy was 1/2 mv squared. So that's the kinetic energy formula. And we know the mass and the velocity, so we know and we have to do the kinetic energy before and the kinetic energy after. Momentum is a vector, so there's going to be 2 equations here for the x and the y. So you'll have 3 equations. You should be able to do it, but my goodness, that's a tough question. I would even, if you couldn't do that, I'm fine. You have to be a math person. Here we go. This is the model airplane traveling. Oh, these are 2 just airplanes. This is a good one because this is now an oblique collision as well. Because one's coming down and the other one's coming down, straight down, and they collide. So there's no right angle triangle here. So this is a little bit harder one. You have to take the components and stuff like that. So this one is a little bit harder. And the trick here is that to keep the velocity in kilometers per hour. You don't have to, but it makes it just all cancels out really nicely. And last but not least, number 6. Impulse needed to change. So it's actually for an impulse one. And there's not a little trick here. This is a direction thing. It says to the northeast. And it's 45 degrees north of east is northeast, in case you didn't know that. Yep, try that out. This one is a good vector one as well. But it's an impulse one. There's no collision. There's only one object in this one. So this one might be a bit of a head scratcher until you go back to the beginnings of chapter 3.2 on impulse. Anyhow, give it a shot. Thank you. Enjoy.